Okay, what I would like to do here is actually a couple of things. I want to talk about the number e, the transcendental number, sometimes called Euler's number, after the Swiss mathematician Leonhard Euler, and then talk about how to use this idea of the number e to come up with a formula for continuously compounded interest by manipulating our formula that we have for compound interest. So, as of right now, the number e is just a button on the calculator. So coming over here, if we calculate e, let's say e to the first power, it's about 2.718. Not exactly, but it's an irrational number, so the decimal goes on forever. But what is the number e? Where does it come from? So I want it to be more than just a button on the calculator that we use without really understanding where it comes from. So by definition, the number e is defined as, well, this quantity here, 1 plus 1 over x to the power of x. And e is what happens to this as we take what's called the limit as x goes to infinity. All this means is x is a variable, x is like an input slot, and as x gets really large, this quantity 1 plus 1 over x to the power of x starts to get closer and closer to one fixed constant. So what I have over here on the left, I'm going to let Excel do this calculation for me because I don't want to do it 9 or 10 times myself. So basically I have some input values for x starting with 1 and ending with whatever this is, 100 billion or something thereabouts. So in this second column, in column B, I'm going to let Excel, well, let's define this cell. And if you haven't used Excel in this way before, this might be a good chance to get some exposure to it. So I want to define this cell to be equal to basically exactly what this formula says, parentheses, 1 plus 1 divided by x. So x is located in that position directly to the left. So to the left of B2 is A2. So I'll say 1 plus 1 over location A2, because that's where my x is, close parentheses, raised to the power of that same x. Okay, so what this is basically doing is Excel is going to take 1 plus 1 over the number to the left, close parentheses, and raise that to the power of number to the left. Okay, so if you replace this x and this x with the number 1 and calculate this out, you get 2. And if I copy this formula down, Excel will apply it to the number 10. So if you plug in 10 for x, you're at 2.59. If we plug in 100, 2.7. Plug in 1,000, 2.7169. Okay, so, and the larger and larger these numbers get, or the larger and larger the input values get, well, you see the final calculation, well, it starts to level off, 2.718, 2.718, 2.718, and by the time we're down here, we're getting 2.71828. So, and this is exactly, if you look at the calculator screen on the right, this is, if the input values get larger and larger, the outputs will start, we'll start seeing this over and over. So, all right, so this is the definition of the number e. It's approximately 2.718, and it comes from this definition, this expression, 1 plus 1 over x to the power of x, as x gets really, really large. So now what I want to do is come over here and see if we could manipulate this formula, our formula for compound interest. Now remember, compound interest has a fixed number of compounds per year, or a fixed time interval between compoundings or between recalculations of the principal. And let me just put over here the definition of E. E is the limit, or basically what happens when x gets infinitely large, of this quantity 1 plus 1 over x to the power of x. Okay, so basically we want this formula on the left to look like this formula on the right. So 1 plus 1 over something to the same power of that something. So the denominator and the exponent need to be the same expression. Okay, so what can we do here? And this is not something I would expect you to maybe do on your own. You're not going to really need to do it, but it's good to understand where these formulas come from. So the first thing I'm going to do is take this r over n, and I want it to be in the form 1 over something, right? So what I'm going to do is basically take the reciprocal of a reciprocal. So if you take a number, let's say, I don't know, we'll take the number 4. Then you take the reciprocal of 4, that's a new number, 1 over 4. But then if you take the reciprocal of the reciprocal, 1 over 4, well, that's equal to, back to where you started, that's equal to 4. So the reciprocal of a reciprocal, two reciprocals is basically cancel each other out. So I'm going to take p parentheses 1 plus, and let me take the reciprocal of the reciprocal, so 1 over n over r to the power of n times t. Okay, so the second line, the line I just wrote, is equivalent, equal to the line, the original formula. Okay, let's get rid of this. Okay, so now I need the exponent to contain an n over r. So now I want to work with this n times t. So what I'm going to do is, we have p parentheses 1 plus 1 over n over r to the power of n over r times t. So basically, I needed a divide by r, so we can multiply and divide by r. That's has a net, again, another net change of 0, but now we have the denominator of the fraction and part of the exponent as being the same value. So now the last thing I'm going to do is split off that part of the exponent that lines up with the definition of e. So 1 over n over r to the power of n over r, and I'm going to take this r and this t and split that off. So I'll throw some more parentheses there and put the rt on the outside. So now we have 1 plus 1 over n over r to the power n over r, and then all of that to the power of rt. So what we've done is we've manipulated the formula for compound interest to contain this, to contain the definition of the number e. So what I have in this green box here is exactly this. So that means as this number, this n over r, whatever this is, so remember n is the number of compounds per year, as that gets infinitely large, this expression in the green box becomes the number e. So we have p parentheses e, and then on the outside of the parentheses we have the exponent r times t. So here's our formula for continuously compounded interest. A of t equals pe to the rt. Basically, it's what happens to this formula as n gets infinitely large, and we end up with this guy over here. Instead of compounding monthly or daily, think about compounding every hour, compounding every minute, compounding 1,000 times a second. As that time between compoundings gets infinitely smaller, the number of compounds per year gets infinitely large, the compounding becomes continuous rather than at a fixed interval. Okay, that does it for the derivation of the continuously compounded interest formula. And the next place we're going to go from here, I'm going to just put it on a separate video, is using this formula to sort of plan for retirement. Think about, based on inflation, which is a continuously changing quantity, based on inflation, what do we have to make per year at retirement to basically maintain the same standard of living as you do today? So Next video, we'll talk about the problem that you're going to be turning in.